This video covers Griffiths E&M section 5.2, problem 5.8. The goal of problem 5.8 is to calculate for a square wire the magnetic field at the center of that wire. We'll say that this wire has a square width of 2R and it carries a steady current I, and we will say that that goes counterclockwise. Okay, so what is the magnetic field at the center? Well, our strategy is to use the Biot-Savart law still. Mu naught I over 4 pi. We have dl prime cross script r hat over script r squared. Okay, it's clear from this expression here that we need to treat each side separately. Okay, as I define dl prime, I know that direction is going to change at every side face. Right? For example, I define some chunk here with dl prime, and on the right face it has to be pointed upwards. Right? So I need to treat each side separately. So let's go ahead and treat the bottom side first and see if we can learn anything from it. Okay. So I have some vector there. Script r points in this direction. I will go ahead and add a dotted line down here. And I'm going to go ahead and acknowledge with symmetry here that that the magnetic field from this little dl prime piece that I drew here and this magnetic field, all right, the horizontal bits are going to cancel. All right, I'm going to be left with just something that points out of the page in the end. Okay, great. So if that whole bottom side has something that just points out of the page, that means that all the other sides will also have the same kind of cancellation. And then I know that if I can calculate the magnetic field from the bottom section of the wire, 4 times that magnetic field will be the total magnetic field from the loop. So I only have to do one side now. All right, so let's go ahead and try to calculate that. Okay, so previously we have done this for an infinitely long wire. That borrowing from that result, I get that this segment of the wire is going to have a magnetic field mu naught I. This is example 5.5, by the way. Mu naught I over 4 pi 1, so the integral here 1 over s cos theta d theta. Okay, in that case, s was the distance from our, the closest distance from our wire to the point we are measuring. Because this whole width is 2r, that means that the distance from point to point here is just r. Okay. So that's mu naught I over 4 pi 1 over r. We also had this direction associated with it. I need to do the integral of cosine d theta. I know that's sine. That's sine of theta. And I need to figure out what the bounds are going to be. Previously we knew we wanted to stretch infinitely far away, so we had a bound of pi over 2. All right. But for a chunk of my square. This is r. This is r. I want to integrate from an angle that goes from here to an angle that goes from here. It happens to be minus pi over 4 and pi over 4. All right, so I can do that. Mu naught I over 4 pi, 1 over r, square root of 2 over 2, plus square root of 2 over 2. And therefore my magnetic field is square root of 2 mu naught I over 4 pi r. Right, but this is still just the value for one of these wires. So we need to go ahead and say that B total is 4 times B, or square root of 2 mu naught I over pi r, pointed out of the page.